in this theory. The interesting limit sigma, and there's a sigma squared term. Sorry. N by 2 before sigma squared. The interesting limit is when I take b4 to infinity, holding m squared by b4 fixed. In this limit, this term drops out. Okay? This quantity that is held fixed, m squared by b4, I'll define as m critical. Okay? And with that understanding, my theory becomes d phi bar d phi plus sigma phi bar phi plus n m critical sigma. So the limit b4 goes to infinity. This is the theory of that. Okay? M critical can be whatever I want. In particular, we could choose it to be 0. In that case, this defines what's sometimes called the nonlinear sigma model, or what you might think of as the UN, the UN analog of the Wilson-Fisher theory for scalars. Okay? As all of you know, a theory of scalars in 3 dimensions has 2 fixed points. There's the free fixed points and there's the Wilson-Fisher fixed point. And this scaling limit here produces the Wilson-Fisher fixed point as a deformation of the free fixed point. I take it before infinity, but not a huge potential. Okay? So this line of theories that I will study has a specially interesting scaling limit. One in which we scale to mass deformations of the Wilson-Fisher fixed point. Okay? And one of the first results that we will see, or that I will okay, I'm out of time, but I will tell you about next. Yeah.
Take a few minutes.
I'll take a few minutes. Yeah. So one of the results that we will discuss in great detail and then examine through the S matrix in my next lecture is this quite remarkable conjecture duality. The duality that's conjectured is that the critical bosonic theory, coupled to Chern Simons theory, okay, at renormalized coupling constant, at renormalized kappa boson and N boson, okay, is dual to the fermionic theory at gauge rank NF and kappa F, provided N and kappa transform under duality relationship. And the duality relation is kappa F is equal to minus kappa boson, and NF, okay, NF is kappa boson mod kappa boson minus N boson. Okay, we're going to claim that at least in the large N limit, and plausibly also at finite N, where these relations have extra ones and halves in them, extra 1 factors of 1 in them, that at least in the large N limit, and plausibly at finite N and K as well, at least large enough N and K, these two theories, the theory of critical bosons coupled to Chern Simons theory, okay, is the same thing as the theory of fermions coupled to Chern Simons theory once we do this flip of parameters. That's going to be the claim. It's going to be a very similar claim to this one, to this kind of shuffling of parameters. Okay, in fact, it's what this reduces to in the limit that m goes to 0. Because k goes to k minus, n goes to k minus n, m, ignore, k goes to k. So it's the non-supersymmetric version of Givion-Kutuzov duality. Okay? But we're going to claim that we, not only is this true, but that we understand much more about why it's true than, and this has to do with anionic physics, as I'll tell you about next time. Okay, I think I'll stop here for questions.
Can this duality derive from some supersymmetric duality then giving us Suzy breaking deformation?
Yes, it can actually, or at least motivated. I'll describe this to you. We wrote a paper on that.
I see. And then you check this duality under all the perturbation theory?
At all orders in Toft perturbation theory, but strictly at large n, unfortunately. Okay, you will see. You will see.
Okay.
I will have to give you details. Okay.
Is there what about for the actual quiver theory? Did it make this m? You got one?
Yes.
A reasonable conjecture?
There's a reasonable conjecture. Again, by definition, you see, it gets more conjectural. But again, you could try to take the supersymmetric theory and sort of deform it the way we did. You know, there are many things that could go wrong, right, in that process. You could develop instabilities, all kinds of things that could go wrong. But if you shut your eyes and blindly did that, there's a reasonable conjecture, which is basically identical to this, apart from extra factors of 1 that have to do with shifts that you get in the Chern Simons level by integrating out the massive fermions. As you know, the way it happens is the first fermion becomes massless on one side and is integrated out. So apart from those factors which you can easily control, there's certainly a reasonable conjecture.
And one could check that perturbative in M.
In M over N, one could check that. Nobody's done that. Yeah, that's a very interesting. Yes?
Can you quantize anions?
What?
Can you quantize anions?
Well, coupling ordinary bosons of fermions to Chern Simons theory is an effective quantization of anions. Yes, so in that sense you can. But, you know, if the question is, can you directly do it? This is hampered by the fact that, you know, anions are never non-interacting. As we saw, the two-particle state for anions was not some Fock space of one-particle states. It had this complicated Aharonov-Bohm scattering matrix in it. Three-particle states are even worse. And this was all with abelian anions. With non-abelian anions, you know. So, then if what you want is an explicit sort of like simple Fock space type representation, which is perhaps what you want, I don't think they exist one. Yeah.
The non-relativistic particles coupled to the non-N Chern Simons, is the scattering integrable? Naively, in a particle picture, it sounds like it would be integrable because it seems like it would satisfy the Baxter equation just from.
Okay, interesting. I haven't seen the comment made and I haven't thought about it. However, one thing I tried myself was to try to solve the n-particle problem. I tried to, you know, for instance, compute the thermodynamics of the system. I wasn't trying to use integrability, but I found it a very difficult problem.
Thermodynamics on what space?
Just on torus. You just compute the density of states.
But even for integral systems, to
actually do something like that.
Finite space is actually difficult. Well, I mean, it's not trivial. Usually one figures out the factorize S matrix first, and then use the try to apply TVA.
Yeah, okay. I should say I don't know, but this is really fascinating. Okay, because as you know very well, since we did some of this together, we have these explicit formulas for the free energy that gives you, after mass deforming, you know, you can take a non-relativistic limit on that, and gives you a very non-trivial answer for the non-trivial prediction for the free energy of a gas of non-relativistic anions. But that's just a problem of Schrodinger's equation. So it would be really nice to reproduce that answer by solving Schrodinger's equation. Nobody's done that as far as I know. Yeah, it would be really nice if one could make progress.
So, strictly speaking, to define the S matrix, I think it sounds like one has to be real careful in ordering the asymptotic states. You cannot just use the usual Fock space representation. You have to say, let's say, take the spatial circle at infinity, you have an ordering, and you maybe have the different sectors in your space.
Yeah, we'll have a lot to say about this in the next lecture. What we're going to say is that there are all kinds of surprises in this S matrix, having to do with the fact that actually you should be attaching Wilson loops to these things. Please make your. You'll have more to say about it after next lecture.
other questions?
But having said that, this is a subtlety that should apply, anyone who studies Chern Simons theory, including people who study scattering in ABJM theory. And, at first sight, you just ignore it, right? But as we will see, because we can do some all-order calculations, if we've not messed up, there are structural surprises in these theories, which I believe will be structural surprises in all theories involving Chern Simons theory, including ABJM theory. Okay, but you up to the next.
From the practical point of view, if you the first try to integrate the Chern Simons coupled to the matter field and then integrate the matter field, it sounds like you would just be, you'll be taking the matter field path integral weighed by
A non-local interaction term.
No, I want to. Well, I want to say that you kind of put in the expression value of the Wilson lines in Chern Simons theory, but okay, that sounds kind of.
That's the other way around, right? You were trying to integrate out the matter. There are two things you could try to do. You could try to integrate out the gauge fields, get an effective theory of matter. Or you could try to integrate out the matter and get an effective theory of the gauge fields.
I meant to fix the word line of the matter.
I understand. But then you want to sum over all word lines, right?
Yeah.
Okay. So that should give you some effective gauge. Generate some effective dynamics of the gauge. Okay, yeah, right.
Yes.
Okay, so let's thank Shiraz again.